Alright, so what we've done here is kind of gone a step further. So now what we're going to do is add a voltage to the circuit. This is a 9-volt battery, as you can see. I basically got that connected up. The positive lead is not connected to the battery. The negative lead is connected in. I've actually put a break in this end, that's so I can measure current, which should be on this meter here. But it's exactly the same circuit that we had looked at before with the 4 resistors. We've got 100k, 1k, 1k and 6.8k ohm resistors. They are in series with each other. What should happen now is that we should see what type of current draw the circuit's got with these resistors in place, and also we should see what the voltage drops are across each of these resistors. Now some of them will be quite low. So just have a recap here. Our series circuit that we were working on before. Now we've added the battery. You can see we've got the positive side on this side, that's the red, and the negative side on this side. Now as you can see here, I've got the arrows going away from the negative, which is electron flow, and moving around the circuit in this direction. Some books will use conventional flow, the arrow will go the other way, but either way it'll work the same. Our total resistance for the series circuit measured, and that was 106.9k ohms. So that's the one that we'll be using because that's actually the measured value, and we've tested and proven that as close to accurate as possible. So if we want to work out what the current is in a series circuit, you can see the current only travels in one direction, it doesn't go anywhere else. So this is a DC series circuit. Right, there's no other path for the current to flow. It has to start at, in this case, the negative end, flow around through the wires, through the first resistor, second, third, fourth, back down through the wires and back to the battery. If you were using conventional flow, it would just do it the other way around. So it doesn't matter which way you go. And we know that I, which is this current, is equal to E over R, so that's your voltage resistance. That can be V. It doesn't matter which way you write it. So I equals E over R or R equals V over R, either way. But our voltage we're talking about here to get the overall effect of the current is the total voltage supplied, which is 9 volts, and the total resistance of the circuit, which is the measured resistance, 106.9k. And you can see here that we have a current flow of 84.2 microamps. So we have 84.2 microamps of current flowing around the circuit with this combination of resistors back into the battery. Now it's not a high current. I didn't want a high current because otherwise you're going to cause other problems. What we can also work out is that in a series circuit you get a voltage drop for each resistor. And as you can see here, this being the larger resistor has the largest voltage drop. These being the smaller resistors, the 1K. You can see here 84.2, 84.2, and this one being slightly higher in value to the 1k ohm resistors has a larger voltage drop than what these would. The larger the resistance, the higher the voltage drop. The smaller the resistance, the lower the voltage drop on that resistor. And obviously if you get a very large resistor in the circuit like this one here, you're going to have the largest voltage drop. Now all these voltage drops should add up to the supply voltage. That's the whole idea of a series circuit. So we're supplying 9 volts, and if you add all these up, and keeping in mind you're just getting slight differences in meter readings, etc., we actually end up with 8.999, which is close to 9 volts as you're going to get with a measured value. So it proves the circuit. It proves that one, current only flows one path. It also proves that the voltage is split between the resistor values in the circuit, as you can see in this row up here. But the current flowing through this resistor is the same as the current flowing through this resistor, the same as that one, the same as that one. So once you know your current flowing in the circuit, you can then calculate the voltage drop across each resistor using Ohm's Law as well. So the first thing we're going to do is just prove that our current calculations are correct. Now, keeping in mind that this is exactly the same circuit that we're looking at before, and because we've calculated that the total current should be about 84 microamps, I've got the meter here set on 100 microamp range, so it should be enough to cover the range that we should be looking at. And if I connect the power to the circuit, you can see that the meter rose up, and if you look down over the meter, you can see that the meter here is reading about 86 microamps. So it's reading a fraction higher than it should, but the point is, this is not a super accurate meter. It's just an indication meter to give you an idea, but it's fairly close. So the first one we're going to have a look at is the voltage drop across the larger resistor, and to do that, right, the multimeter or the digital multimeter is set to DC. As you can see here, we're reading a DC voltage, and I've got it set to 20. That's the lowest value on this meter that I can measure the voltage drop across here. Now, it's important you get the leads around the right way, not so much on these meters because it'll just give you a negative value. But if I go across that resistor, so we're getting 8.4 volts across that resistor, and our calculator was 8.25, which is pretty close to right what it should be. Alright, so we're going to measure the first of the 1K resistors. As you can see here, I've dropped the meter down to 200 millivolt range, and if I measure that one, you can see I'm getting 85 millivolts for my reading, and the calculation was 84.2. You are going to get slight variations. The next one should be close to it as well. It's a 1K resistor. So you're getting 84.9, and again we calculated 84.2. And the final one, which is a 6.8K, I'm going to have to go up range. So we're going to the 2 volt range now because it's over 200 millivolts. And this one is 586 millivolts, and we calculated 573. We did our calculations with a 9 volt battery. These are the values that we got using our current that we calculated. And the way that we got these values was using Ohm's Law, E equals I times R. So I is the current in the circuit, which is this current here, and R is for each of the resistor values. So you multiply 84.2 microamps times 100 k ohms, and that'll give you that value, and then do the same for 1 k ohms, and again for 1 k ohms, and then again for 6.8 k ohms. So if you do that, you come up with this value, which is what we worked out before. Now, when we did the measured values across each resistor, you can see here we've got 8.4, we calculated 8.25 based on that current. And again we've got 85 millivolts measured, 84.2 calculated, 84.9 measured, and then we had 573 calculated, 586 millivolts measured. If we add all that up, we end up with 9.1559 volts, measured. So the voltage drops across the circuit has to equal the supplied voltage. Now, the measured supplied voltage is 9.24 volts. So you can see here that we've got 9.1559. Now you are going to have losses in the circuit. You're going to have variances, with reference to their connections in the circuit. So each connection you've got here, like we've got one from here to the battery, we've got one between each resistor and the leads, etc., etc. So you are going to get slight variations when you go from a theoretical calculation to a practical measurement. And even with practical measurements, just moving around the measuring leads at certain points, you may get slight variations as well. In essence, the important parts from this is that in series circuits, the current is the same throughout the circuit, and the sum of the voltage drops will equal the supplied voltage. As we basically proved here and here with reference to our theoretical calculations and our practical measurements. The point to take away from this, as far as what a series circuit is a voltage divider. So current doesn't change, the values of the drops on each resistance value will change.